So I repeat, for no failure in the member or a machine component or a part, the total strain energy per unit volume in the member due to general loading condition should be always less than the total strain energy per unit volume in the material under uniaxial loading condition. Try to put that in a math form. So, right. So the total strain energy, say from the stress strain curve, so far we are choosing the criteria as yield. So the total strain energy up to this point is this area under this curve. So which is nothing but the area under this curve is of stress into strain. So this is the total strain energy of a material under uniaxial loading condition. So now again we know that the strain from the Hooke's law can be written as stress by Young's modulus, then it will be reduced to of sigma square by E. Since we are calculating the values corresponding to yield, so this equation can be turned to sigma y square divided by E. So that is the total strain energy per unit volume of a material under uniaxial loading condition. So the unit is joules per meter cube. So for example, if it is a stress into strain, for stress it is Newton per meter square, it is dimensionless. So it is Newton per meter square. Actually it can be mentioned as Newton meter divided by meter cube. The Newton meter is a joule per meter cube. Joule is a unit of energy, energy per meter cube. So Newton meter per meter cube can be reduced as Newton per meter square. So that's we say that the product of stress into strain is the strain energy per meter cube, right? So for uniaxial loading condition, so now it is very clear, the total strain energy is half sigma y square divided by E, right? Now we'll try to put this for a triaxial loading condition. So the total strain energy will be equal to half sigma 1 epsilon 1 plus half sigma 2 epsilon 2 plus half sigma 3 epsilon 3, right? So now from this, so 1 by 2 I can take it as common here, and it is sigma 1 into, you all know the strain 1 can be written as sigma 1 by E minus mu sigma 2 by E minus mu sigma 3 by E. Similarly, plus for other two terms, sigma 2 into epsilon 2 can be written as sigma 2 by E minus mu sigma 3 by E minus mu sigma 1 by E. This is the effect of lateral stress on sigma 2 direction. That's we discussed earlier in the session. So similarly, plus sigma 3 into sigma 3 by E minus mu sigma 1 by E minus mu sigma 2 by E. If I try to simplify this, if we try to simplify this equation, then this can be written as, first I will try to reduce to biaxial loading condition, because our interest we are solving for all biaxial cases. So this term sigma 3 will not be there in biaxial and total term will not be there. So the equation will be reduced to of sigma 1 into this E will be common, sigma 1 plus sigma 2 minus 2 mu sigma 1 into sigma 2. And similarly for this will be a sigma 2 term, so I can write it as sigma 1 square plus sigma 2 square minus 2 mu sigma 1 into sigma 2. This is the total strain energy of a member which is under biaxial loading condition. So according to this theory, this should be lesser than or equal to the total strain energy in a material under uniaxial loading condition that we calculated as sigma y square divided by 2e, right? So if I simplify this equation, 2e will be cancelled on the either side. It will be sigma 1 square plus sigma 2 square minus 2 mu sigma 1 into sigma 2. For a maximum limit, it should be equal to sigma y square. So this is the mathematical equation which we derived for maximum strain energy theory. So if we try to develop the region of safety for this equation if we further simplify, we will get a look like sigma 1 square by sigma y square plus sigma 2 square by sigma y square minus 2 mu sigma 1 into sigma 2 divided by sigma y square is equal to 1. And this is nothing but the equation of an ellipse. So for the region of safety, we will get an ellipse with an inclined fashion. Which is sigma 1 and sigma 2, and whichever the stress which is induced in the member which falls inside this curve is safe, and if it falls outside, the material is said to be unsafe. So right, so according to this theory, whatever this is the case, the sigma 1 square plus sigma 2 square minus 2 mu sigma 1 into sigma 2 is equal to sigma y square, right? So let me summarize the maximum strain energy theory. According to maximum strain energy theory, the total strain energy per unit volume induced in the material under biaxial or triaxial loading condition should be less than the maximum strain energy or maximum or total strain energy per unit volume in a material under uniaxial loading condition. So with that theory, we derived the total strain energy, which is nothing but of sigma 1 epsilon 1 plus of sigma 2 epsilon 2 plus of sigma 3 epsilon 3 corresponds to principal axis 3. And with this information, we reduced this equation in the form sigma 1 square plus sigma 2 square minus 2 mu sigma 1 into sigma 2 must be lesser than sigma y square by 2e. This is the total strain energy per unit volume for a uniaxial case. That's it. Now we'll see what maximum shear strain energy theory says, or that can be mentioned as maximum distortion energy theory. And also I want to say the scientist name, which is von Mises. It is also called a von Mises stress theory. So we'll see it. This is just maximum shear strain energy theory.
This video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
Right. According to this theory, the maximum shear strain energy or the maximum distortion energy in the member under a biaxial or triaxial loading condition should be less than the maximum distortion energy or shear strain energy in a material under uniaxial condition. So right, we'll explain this theory. What is the difference between maximum strain energy theory and maximum shear strain energy theory? Before going into that, this theory is so important because it gives more accurate result for a material which is subjected to a pure shear, even for ductile materials. And this theory is also called as von Mises stress theory, and each theories are having a other name, but here I am more specifically I am telling this because the student may often see this theory in any design tool like ANSYS or Abacus. So maximum shear strain energy theory, why it is so important? So the total strain energy is having a two components, which is a volumetric strain energy plus a distortion energy. And von Mises says that this distortion energy is the energy which makes the material to shear, and where this is not contributing for shearing the material or distorting the component. So let me explain this. The total strain energy is the volumetric strain energy plus distortion energy. So first, volumetric strain is nothing but the strain in a member which corresponds to hydrostatic loading. Hydrostatic loading in the sense that the stresses will be acting in all the directions with the same magnitude. So in this case there will not be any distortion in the component. So this will happen usually if I take a stress strain curve of a ductile material in this elastic region, more precisely this volumetric strain will happen. So there will not be any distortion in the material. Distortion in the sense for this same phase, this kind of deformation will not occur in the volumetric strain part. So von Mises says that this strain or the volumetric strain or due to hydrostatic loading will be usually occurring in this region, so up to an elastic point or where it ends. Once it starts yielding, then the material will goes to distortion. So von Mises says that instead of calculating the total strain energy and comparing with the uniaxial case, calculate the strain energy which corresponds for the distortion, and that energy will be the exact energy for the failure. So according to this theory, so the failure cases or for no failure, the maximum distortion energy induced in the member under uniaxial loading condition should be less than the maximum distortion energy in a material under uniaxial loading condition. Right? It is quite logical. So let me try to put in the math form and we'll try to find the region of safety. So total strain energy which we have just seen, so of sigma 1 epsilon 1 plus of sigma 2 epsilon 2 plus of sigma 3 epsilon 3 is the total strain energy, so which we already knows from this previous class. So I'll try to calculate the volumetric strain, and from the total strain energy, if I subtract this volumetric strain energy, then I will get a distortion energy. Then we'll compare this distortion energy of a biaxial case with the uniaxial case and we'll find the region of safety. Right. So now, so the volumetric strain is so simple again, which can be written as half sigma v into epsilon v, and this sigma v can be written as average of all three stresses acting in all three directions. So sigma 1 plus sigma 2 plus sigma 3 divided by 3, and epsilon v has to be calculated. So epsilon v is again so similar, sigma 1 by E minus mu times sigma 2 by E minus mu times sigma 3 by E plus sigma 2 by E. This strain arises from Hooke's law, and the strain in the longitudinal direction is decreased corresponds to the strain in the lateral direction. That is included here to get the strain in a principal axis sigma 1 and the strain in the principal axis sigma 2 minus mu sigma 2 mu sigma 3 by E minus mu sigma 1 by E plus sigma 3 by E minus mu times sigma 1 by E minus mu times sigma 2 by E. So this is epsilon V. By substituting this epsilon V here, then we will get what is total volumetric strain energy. So I'll cut my derivation here, so I don't want to extend just to show the mathematical part. I'll directly write the final equation, which is called as usually the von Mises stress or the strain energy density or distortion energy per unit volume. So that is written as so now you know what is maximum shear strain energy theory. Instead of comparing the total strain energy, we are comparing the distortion energy with the uniaxial case, right? So the total shear strain energy or distortion energy, UT is written as UV plus UD. So UD is UT minus UV. From this total strain energy we calculated, then I have shown the equation for the volumetric strain energy. So the distortion energy is calculated as, by substituting all those terms, it will reduce to 1 by 12G sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 1 minus sigma 3 whole square. So this is my distortion energy by substituting all the values. I am not showing those equations. Just by showing the equation, I am directly choosing the equation here, which I have already derived. So G is here the shear modulus, where E is the Young's modulus. So it is having the relation E is equal to 2G into 1 plus Poisson's ratio. So I deduce the E, which to reduce the equation, which comes to E is equal to 2G into 1 plus mu. I'll summarize this equation as this. This is the total distortion energy. So now I'll try to reduce this to an biaxial loading condition, where we are solving all the equations for biaxial condition. So it will be reduced to 1 by 12G in biaxial sigma 3 will not be there. So it will be sigma 1 square plus 2 square minus 2 sigma 1 into sigma 2 plus sigma 2 square plus sigma 1 square. So this can be again simplified as 1 by 12G 2 sigma 1 square plus 2 sigma 2 square minus 2 sigma 1 into sigma 2. So this can be further reduced. 2 can be taken common out. So 2 will be getting cancelled, and this will be 1 by 6G sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2. This is the total distortion energy induced in a member which is under biaxial loading condition. So as per the theory says, this distortion energy should be always less than the distortion energy which is induced in the member in a uniaxial loading condition. So right, with the same equation, with the same it fall down. You note down the timing. No, it fell down.
Just turn this way.
No, this side I think. Right. So now this is the distortion energy in a member under biaxial condition. The same thing we can write for a uniaxial case. It is going to be 1 by 12G right. So as I said that this is the distortion energy for biaxial condition. Similarly, we can write the distortion energy for uniaxial case with the help of this equation. So where sigma 2 is also not going to be there and sigma 3 is also not going to be there, then it can be reduced to sigma 1 square.
This video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
And in this term again one more sigma 1 square is there. So for uniaxial case, the distortion energy is 1 by 12G 2 sigma 1 square, which is 1 by 6G sigma 1 square. So you all know that the principal stress here in uniaxial case we are calculating for the yield point, so it can be changed to sigma y. So right, so this is the distortion energy for biaxial and this is the distortion energy for uniaxial, and the theory says this should be always less than this distortion energy which is occurring in uniaxial condition. Now I'll put that in the equation form. So 1 by 6G sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 for a maximum limit is be equal to 1 by 6G sigma y square. Right. So being cancelled, sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 is equal to sigma y square. So this equation can be further reduced to get the region of safety. Sigma 1 square plus sigma y square plus sigma 2 square by sigma y square minus sigma 1 into sigma 2 divided by sigma y square is equal to 1. If this term gets here, if this term gets down to the denominator in this left side. So now by looking this equation one can conclude that this is the equation of ellipse. So the region of safety for von Mises stress theory is again an ellipse with the given parameters drawn using the given terms which we have derived. Sigma 2 and sigma 1, the stresses which falls inside this boundary is said to be safe, and which it falls outside is said to be failure. Right. So again I will explain you why this theory is alone so important. As I said before, when it compares with the maximum strain energy theory, the maximum strain energy theory says that it compares actually the total strain energy for the failure criteria. But from the experiment we know very well that the material discharge only at the yielding. Before that it will undergo only a volumetric strain, or it just react like when the load is acting as an hydrostatic loading. So there will not be any distortion. So as von Mises proposes that the distortion energy, if you calculate and equate that with the strain energy density or shear strain energy or the distortion energy in a member under uniaxial loading condition, it will be so logical and it will give so accurate result. And that can be also concluded in pure shear case. When the member is subjected to pure shear, as per von Mises stress theory, based on this equation which we developed, will reduce to this tau max will be equal to sigma y by root 3. For pure shear case, the sigma 1 will be equal to tau and sigma 2 will be equal to minus tau. That's what those who understand the principal stresses very clearly may know that I'm not going deep into that. The sigma 1 will be equal to tau and sigma 2 will be minus tau. And substituting those values here, then that maximum shear will be equal to sigma y by root 3. And this what we accurately will get in the experimental. When you do experiment, the maximum shear stress will be equal to the yield divided by square root of 3. So again this equation also will give the same value, and that's we conclude that this shear stress, maximum shear strain energy theory will be more accurate, will give more accurate result better than maximum strain energy theory, also when you compare with maximum shear stress theory. Where maximum shear stress theory we will not get that tau max is equal to sigma y by root 3 for the pure shear case. But sometimes you may use maximum shear stress theory for the problem which for a material which undergoes which plastically deform or a ductile, or even a pure shear case. Even maximum shear theory, stress theory also can be used, and one versus stress theory can also be used, but one versus stress theory will give more accurate result. Due to the case, we will choose the distortion energy as a failure criteria. So here we conclude this failure theories, the various failure theories. It is proposed because the various properties of the materials which we have, like yield strength and ultimate strength of the material, are based on the testing which is uniaxial, which is based on uniaxial loading condition. But in the real time it may be biaxial or triaxial case. Then if you want that material is said to be failed, or the machine component is failed in triaxial or biaxial case, then we have to study all these theories. And in the next session we may go deeply into which theory will be suitable for suitable loading condition and for the ductile and for the brittle material. Thank you.
For more updates, stay tuned to KL Radio, the voice of KLians. This video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.